Okay, so I'm just going to talk through solving this first one using the rational zero theorem. So we'll talk through possible zeros. Maybe we should mention some shortcuts because shortcuts are always good. And then we'll culminate with graphing. So possible zeros is where we're going to look into the P and Q idea. So we'll try that out. So P over Q. We remember P is tied to the factors of the constant term. So in our example here, that would be factors of 40. So yes, I know that's a lot of factors, but I thought it would be nice to work through a hard problem together. I know at least one person feels like the examples and the videos are too easy and the homework's too hard. So I thought I would do a pretty much as bad as it could get, right? So factors of 40 would be 1, 2, 4, 5, 8, 10, then we got to jump around for a little while. Let's see, we pop all the way to 20, and then I guess 40. So that should be all the different factors of 40, including the plus and minus, since we could multiply two negatives to get to 40 or two positives. And then factors of Q are always tied to factors of the leading coefficient, which here is understood to be 1 based on the x to the fourth term. So that has a leading coefficient of 1. So the nice thing about Q in this case is factors of 1 are just plus or minus 1. So it really doesn't change the list of factors for P. And depending upon who we are and how we see things, some of you may want to list out the plus and minus separately, or maybe you're content with my list. But just to be as clear as possible, I'll go ahead and list them out literally one by one, just so we all agree that the plus or minus really implies two different options. So again, if you're satisfied with plus or minus, it's a little bit more efficient, but I'm going to be really thorough and list them all out here, partly so that we get overwhelmed together, because it's more fun to get overwhelmed together than on our own. So hopefully we have all the factors of 40. So that means we just found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible zeros, which is a little overwhelming. We know based on the degree of this polynomial that there are only 4 zeros, right? It's a degree 4 polynomial. So there are at most 4 rational zeros, but remember sometimes zeros could be irrational or imaginary. So in this list of 16 possible zeros, these again are referring to the rational zeros. So that's one important thing to note, is that you can have zeros that are rational, which the rational zero theorem will help us find, or they could be irrational or imaginary, and we'll see some of that before we're done for today. So if you're just diving in, kind of getting used to this process, you can literally start at the beginning of the list and work your way through. I'm going to go ahead and demonstrate that because I'm thinking that's what a lot of us are doing. And then we'll go ahead and talk about some shortcuts or ways to make the process a little more efficient. So I'm going to start in at my first zero in the list, which was x equals 1. And to try that as a possible zero means set up the synthetic division from the original polynomial. So I'm going to put my placeholders of 1, -6, -5, 42, and 40. So just as a reminder, those come from the coefficients from the original polynomial. And then we're dividing by x equals 1. So probably everybody's comfortable with this process of dropping, multiplying with the value out front, adding down the column, multiplying, adding again down the column, multiplying, adding, multiplying, adding, and then we get this remainder at the end, which here it looks like it's 72. So our desired remainder, of course, is not 72. Our desired remainder is 0. So since we did not get a remainder of 0, this is not going to work. So x equals 1 is not a 0. And we know that because it didn't go in evenly. We didn't get a remainder of 0 when we did our synthetic division. So it can be a little discouraging at first when you get a non-zero remainder, because then you're like, all that work for nothing. But let's just keep plotting through our list. Again, I'm just trying to mimic the process that a lot of us are going through. So the next value in my list is -1. So again, I'll set up the synthetic division. Same placeholders of 1, -6, -5, 42, and 40. This time I'll use our -1, and we'll walk through that process of dropping, multiplying, adding, multiplying, adding, multiplying, adding, multiplying, and one last addition this time gives us a remainder of 0. So if you're fortunate enough to get a 0 on try 2, then life is pretty good. I know some of you have had to do 5 or 6 or 10 tries to get a first 0, so it can be a little bit tedious. So this is good news that x equals -1 is a 0 since we got that remainder of 0. The great thing about this process is once you find your first 0, you can always build off of the remainder. So you don't need to continue going back to the original polynomial, but instead work off of the more simple polynomial that remains. So again, a couple different options here. I know, Hala, right, you've been graphing in Desmos and kind of using that tool to assist you in making good choices. So some of your classmates may benefit from that strategy as well. Technology is available to us. Desmos is a free resource, so I don't think that's a bad idea to graph it and almost like work backwards. So you guys are going to have to be able to show the process to get to that result. But maybe for this first example, I'll continue working independent of technology in case that's your preference. So I am going to actually just continue plotting through my list and hope it doesn't take me 16 tries. So again, just to recap what we've done, we tried 1, it was no good. We tried -1, and that was a 0. Now let's try 2, and then we'll try -2, and we'll just kind of press forward for a moment. And then pretty quickly here, I'm going to step back and say, what does our polynomial look like based on the factors that we're finding? So let's try, next in our list was 2. So I'm going to try x equals 2. And here's where things get a little fun. I'm going to build right off of the synthetic division that's remaining from the last process. So I don't need to start back over from the beginning. I'm going to build off of the remainder from our 0 of x equals 1. So here we're trying 2. Go through that synthetic process. So I'm going to drop, multiply, add, multiply, add, multiply, add. Let's see, what's that make 24? Multiply. Oops, sorry, I guess I'm done actually. I went too far. So this is now our remainder, right? Because this column is technically gone as we embark on our second iteration. Whew, so we get to a remainder of 24, which again is not 0. So that tells me x equals 2 is not a 0. So again, kind of a bummer, but the synthetic process moves fairly quickly. So I just am going to put a little X up here to say, nope, that one didn't work. And what I'm going to do, because I have the easy luxury of erasing easily, is I'm going to back up my work for +2, try changing it to a -2, and just see if that works. So +2 was not good. So if I just make a little bit of space here, I'm going to kind of make use of my synthetic division that was already set up and change the value to -2. Again, if you're writing on paper, you can just start it over. So let's go ahead and try -2. I'll drop the first value, multiply, add, multiply, add, multiply, and add to get, aha, a remainder of 0. So this problem is fairly nice. We tried 1, it didn't work. We tried -1, it worked. We tried 2, didn't work. -2 works. So far we're 2 out of 4, and that's pretty good when you think of this rational zero theorem. So this means that x equals -2 is another 0 of the polynomial. So hopefully in terms of the synthetic division process, we're feeling comfortable. This is maybe a good chance for us to step back and say, based on the original polynomial, what do we know? Because it was degree 4. We've found 2 zeros so far, so the remainder is a degree 2 polynomial, and we have other techniques to break down quadratics, right? We could think about factoring or quadratic formula. So let's take a moment. I'm just going to add a little bit more space here. Let's take a moment and put a summary of what we know. So our original polynomial, just to summarize where we are, was f of x equals x to the 4th minus 6x cubed minus 5x squared plus 42x plus 40. When we found our first 0, it was x equals -1. And x equals -1 implies the corresponding factor would be x plus 1, right? If you have a factor of x plus 1, that creates the 0 of x equals -1. And when we divided by that x equals -1, the remainder, it's a little hard to see in all my scribbles up here, but the remainder was just this quantity here. So I'm going to carry that down, and that would be x cubed minus 7x squared plus 2x plus 40, because the remainder is always 1 degree less than what you started with. Then we divided again, and when we were successful, it was the 0 of x equals -2, which has a factor of x plus 2. So the second 0 that was an actual 0 was -2. And if x equals -2 is the 0, the factor that would cause that 0 would be x plus 2. And then what remains is this last line you can still see here, which would be a degree 2 polynomial. So that's going to be x squared minus 9x plus 20. So based on the order in which I found my zeros, which could be very different from the order in which you find your zeros, I have 3 factors right now: a linear factor, and a quadratic factor. So my personal preference at this point would be just to use my knowledge of quadratics to break this down rather than to continue with synthetic division. So for me, once I'm at quadratic, I just use old techniques. I stop doing synthetic division at that point. Again, it's just personal preference. So many ways to do these, which is both fun and frustrating as you're learning. I do realize that. So if you're struggling with how you like to do things, maybe you can use the process we're discussing here as a model. And then as you get more comfortable, you can kind of be a little bit more free-form about it. So to finish this off, it looks like it does factor to me, because 2 numbers that multiply to 20 while summing to -9 sound like a -4 and a -5, right? -4 times -5 is 20. And then the sum of -4 and -5 is -9. So based on my fully factored polynomial, I can see there are 4 zeros. They are all rational in this problem. I know in the homework sometimes you'll get them to be all rational, or sometimes you'll get some imaginary or irrational zeros. So let's just state our zeros so that it's clear. And I'll go in order from the way my factors are. I see a -1 from this first factor. I see a -2 from this second factor. Those are the 2 we found through synthetic division. And then we just found x equals 4 and x equals 5 by breaking down the remaining quadratic factor. So we did expect to get 4 zeros, and these are the 4. So again, this was just one way to work through this problem. Notice I was able to do this fully without technology, and maybe for the second one, I'll show how you can introduce technology to give yourself a nice head start on the process. So can be long, but hopefully it feels semi-rewarding to actually find those rational zeros. So that's about it for that one. What I want to do next is similar to what you see in the homework, which is now that we've done that work of finding the zeros, let's just draw a rough sketch. We'll use our knowledge of the zeros combined with our knowledge of end behavior. So I'll do that here. Maybe what I'll do is I'm going to steal my work here so I don't have to write it again. So it said, using our work done, that should say in number 1, sorry, in the first problem we just did, we will draw a rough sketch of the polynomial. So I'll carry down those 4 zeros. And this is where I also need to bring up a topic from really last week even, which was multiplicity, right? We understand a little bit about the multiplicity of a 0 tells us whether it's going to bounce or cross through the x-axis at that location. Since it's a degree 4 polynomial and we got 4 distinct zeros, each of these zeros has just a multiplicity of 1. So that means at all 4 of these zeros, we are truly just cutting through the x-axis. We won't bounce because they all have an odd multiplicity. The other thing that I'm going to need to pick your brains about before drawing the sketch is, what do we know about the degree of the polynomial? And what do we know about the end behavior? Sorry, the leading coefficient. Because those two values will determine the end behavior. So the degree is the highest power, which you can tell here was 4. We've talked about that a couple times. And we care mostly about, is it even or odd? So 4 should be even. The leading coefficient is just 1 in this case. And we just really care about, is that value positive or negative? So 1 would be positive. So a polynomial with an even degree and a positive leading coefficient is going to have both ends up, right? If it's even, the ends do the same thing. Even with a positive leading coefficient means both ends go up. So I think based on all the kind of scribbles that we have on the screen, we can produce a really good rough sketch of this function. And I'll go ahead and walk through that just so when you do the homework problems, you have confidence in what we're looking for. So I'm going to make enough space on my x-axis to show the 4 zeros that we found. I'm not going to stress about the y-axis scale, so I'm really just trying to get a basic shape of the graph, not too concerned about scaling in the y direction, unless you want to find like a y-intercept. But let's put down our zeros at -1, -2, 4, and 5. Okay. And then based on this end behavior, I'm going to go ahead and fill in the left side of the graph needs to go up from that last 0. Similarly, based on the right end behavior, my last 0, it needs to go up from there as well. And now to connect the remaining points, I need to keep in mind that for each 0, I'm cutting through. So for example, at -2, since I'm above the x-axis on the left side, I must cut through it on the other side. So I can't bounce like that because that would be even multiplicity. So I keep going through, and then I need to come back up through x equals -1. Since it's odd multiplicity, make sure to go ahead and cut through there. And then again, my scale is not shown, so this is not perfect, but I know I need to come back down to 4, cut through that, and then I better pop back up through 5. So I think you would agree that at each of these x values, I have an odd multiplicity because I'm cutting straight through the x-axis. We have the correct end behavior for an even degreed positive leading coefficient polynomial. And that's what I'm looking for when it says give a rough sketch. So this would be a great time, if you hadn't already, to throw it into Desmos, make sure your graph looks similar in terms of the ends and the zeros. So I'll just show my Desmos graph real quick. Of course, the scale is a little different, but I'll just tap on the zeros to verify with you all we found those same 4 zeros. And as was pointed out by Hala, this is kind of like a W-shaped graph. So you can adjust your scale until it looks pleasing to you, but our ends go up just like the Desmos graph. And again, we had those same 4 zeros, which you can just easily click or tap on in Desmos. So that would be it for that one. So hopefully that makes the process a little bit more clear. And let's see, I'm just going to pull up the homework real quick because I know I made examples that felt similar to the homework. So let's see. In the homework, this of course would be a similar process to what you're doing in problems 19, problems 20, 21, 22, 23, so kind of relates to all of those ones. And then I do have one more because in problem 24, you're going to encounter imaginary zeros, so I wanted to do one like that as well. So, Hala, you're still there? Yeah? Should we talk through number 3? Okay, perfect. Let's just do it together. I'll take your work if that's okay. So you started with possible zeros, and then I'm gonna take your shortcut, and we'll share your shortcut with your classmates as well. Okay. Yeah, factors of, yep. Okay. Good. Yep. Excellent. So those are the factors of p, the constant at the end. And then how about your factors of q for this one? Good. Perfect. So in this case, since p and q had more than just factors of plus and minus 1, we can spend a little time simplifying. Good. And in case anybody is struggling with how to simplify, kind of how I think about it is just walk through, the 1 over 1, the 2 over 1, the 4 over 1, the 8 over 1. So I'll just write those out real quick too. So I'm working just with the factor of 1. And everybody's going to feel comfortable with different amounts of writing. Some of you will recognize dividing by 1 doesn't change it, so I really don't need to show. Yeah, so that just really means plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So then what I'm missing from my list is I still need to show, yeah, good, the dividing by 2. So now I'll take each of the numerator terms and divide by the 2. So it looks really crazy for just a second. So 1 divided by 2, 2 divided by 2, 4 divided by 2, 8 divided by 2. And then I'll reduce those down real quick. So I heard half, then we'll get 1, 2, and 4. And what did you do, Hala, at this point? I know you may have shown your work a little different, maybe not listed out as expansively, but what do you notice in my list of possible zeros? Perfect. So we ended up with some duplicates, so no need to write these duplicates of plus or minus 1, plus or minus 2, plus or minus 4. Good. Perfect. So that narrows us down a little bit to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible zeros. Still quite a few. So in case anybody's not seen the 10 zeros that we see, I'm just going to remind you that the plus or minus really gives us 2. So I think a lot of you are happy with the plus or minus notation, but technically that may be more satisfying to list them all out. So 10 possible zeros. How many actual zeros will we find in this one though? 4, good, yep, four zeros. And with those 4 zeros, right, it could be some rational, maybe some irrational, maybe some imaginary. So we have to be a little careful there. So just because these are all rational in our list, it doesn't mean that all the zeros have to be rational. Okay, cool. I'm going to turn it back over to you, Hala, because I know you are comfortable with the next step. What'd you do next? Perfect. Good, excellent. So let's go ahead and walk through that for the class here. So if you feel overwhelmed by your list of possible zeros, as most of us will, there's nothing wrong with the use of technology to help give you a push in the right direction, right? You guys are allowed to use Desmos for homework, for quizzes. So I'm going to do the same thing. I actually already have it ready to go in Desmos, so I'm going to show you what this original function looks like graphed. and then we'll be able to see what you're sharing with us. So let me do that real quick and zoom back in. So this is the graph of the problem we're currently working on. And what we just heard is that we can tap on our zeros and know in advance what the rational zeros are. So it's kind of like we're looking at the end of the story, even though we're sitting at the beginning. And knowing the ending, we can then fill in the steps in between with our work, right? So, okay, good. So I'm just going to screenshot this so I can scribble on a little bit. But this shows that there are two rational zeros. And let me zoom out so that everybody agrees that there are no more times that we cross the x-axis, right? Nobody sees any other places that we cross the x. So how do we explain the fact that there are only two places where we cross the x-axis, even though it's a degree 4 polynomial? What does that mean? If there's only two rational zeros, yes, good. There must be two imaginary zeros, because what we're graphing on is the real number plane, so we won't see imaginary zeros. Good. Okay, so let me go back to our work here, and I'll just kind of write a little note about what we just said. We're going to use Desmos for a hint. So I worked the first problem without this, but this is just kind of a nice, helpful way. So let me grab, if I can find it. There it is. The work that we just did in Desmos. And what Desmos gave us the hint for is it says if you synthetically divide by -2, you'll get a 0. And if you synthetically divide by -1/2, you'll get a 0. So we're still going to show our work and prove that, but Desmos is giving us a good choice so that we don't have to walk through those 10 possible zeros, right? It's just kind of an efficiency thing. Okay, good. Yep. And I heard you divide it by -1/2 first and then by -2. Perfect. Yep. And the cool. Oh, okay. Okay. Yeah, perfect. The cool thing about the zeros is the order in which you divide by them doesn't matter, and so that's why in this last example, but I know you had found some good techniques as well, but in this last one, somebody else could have had a very different second, third, and fourth step than me, or I guess, yeah, but your end result of the zeros are the same. Yep. Yep. So for example, somebody else may have divided by -2 first and then maybe 4. So the steps of factoring could look different, but the final solution will match up. So that's just a little fun thing to keep in mind. So with where we are in this problem, maybe just to do it a little different, then you all choose -2 first, just so that my work is a little different, and we'll still get the same end results. So let's go ahead and start with -2. I'm going to use the same language I did in the first example. I'm going to say try x equals -2, but it's kind of like we already know that it works. So it's definitely a good choice. So our synthetic division from the original, just to go back up here, I'm going to be snagging my coefficients of 2, 5, 10, 20, and 8. 2, 5, 10, 20, and 8. And we'll divide by that -2 or the -1/2, doesn't matter. So I'll just walk through dropping, multiplying, adding, multiplying, adding, multiplying, adding, multiplying, and hooray, we get the remainder of 0, which we wanted to happen, so that's good. So that means x equals -2 is a 0. And then from there, we may as well just continue building off of the remaining polynomial. Struggling with my words there. So let's go ahead and try x equals -1/2 right from there. So let's try x equals -1/2. This will be fun to use a fraction in the midst of our synthetic division. So we will drop our first value. Multiplying 2 by -1/2 gives us -1. We'll add to get 0. We'll multiply to get 0. We'll add to get 8. Multiplying 8 by a -1/2 gives us -4. And so our remainder there is 0. So this implies that x equals -1/2 is a 0. Okay. Perfect. So that probably matches up, Paula, with your work in terms of the two rational zeros, right? Then from there, it might be fun to see if we can, again, summarize what does this mean about the polynomial. So if I write out the original function we started with again, let's see, it was a 2x to the 4th plus a 5x cubed plus a 10x squared plus 20x plus 8. And based on the order I showed my synthetic division, my first factor would have been x plus 2, because our first 0 was x equals -2. And when we synthetically divided by -2, the remainder would be 2x cubed plus x squared plus 8x plus 4, that orange highlighted row of coefficients. Then next, I would have a factor of, let's see, it would be x plus 1/2, I could say. And because that would produce the 0 of x equals -1/2. And then my remaining polynomial is down to degree 2. Coming from this line of 2, 0, 8, I would have a 2x squared plus a 0x plus 8. So that would be showing just step by step what those different zeros mean about the factored form of the polynomial, just to make sure we're all realizing the connection between the zeros and the factors. So from there, again, we already know these zeros of x equals -2 and x equals -1/2. We had already stated those with our synthetic division. But what remains is quadratic, and this time it's kind of on the one hand more simple. So let's just work this using our square root property. So if we set 2x squared plus 8 equal to 0, because there's only two terms, right? A good technique when you have a squared term and a constant is to move the constant over and then isolate the squared term and then square root both sides. And this is where we had started talking about that imaginary number. So you can see the imaginary number coming in right here. Because if we square root -4, we would get plus or minus 2i. Because the square root of 4 is 2, and the square root of -1 is I. So just a friendly reminder that when you think about the square root of -4, if it helps your head, you can break it up into the real and the imaginary part. Square root of 4 is 2, and by definition, the square root of -1 is I. So that gives us two more zeros technically, because we have plus or minus 2i. If you recall from last week, we talked a little bit about how imaginary or complex zeros always come in pairs. So you'll never have an odd number of imaginary zeros. So just to write this out a little bit more clearly, we get 2i and we get -2i. So that in total, we do have 4 zeros for this polynomial. And we anticipated 4 because of going back to the degree of 4. So, Paula, how are we doing? Still pretty good?
Oh yeah.
Oh yeah, okay. Good, perfect. Nice, good. And even if, step-by-step process different, totally fine. That's gonna happen from person to person. It's more about the end result that matters for sure. Cool, so same as our first example, I'm just gonna end by graphing this one, and then I'll share the link with the class in case anybody wants to get a little bit more homework help. So this is, I think, a good review for, what was it, 19 through 25 on the homework? Yeah, those last couple problems are all about the rational zero theorem. So I think we go on from here just to draw a rough sketch. So I'll go ahead and just carry down the zeros we just found. So we found -2, x equals -1/2, x equals 2i, x equals -2i. And let's also comment real quick on the degree and the leading coefficient, because it's the combination of zeros plus this that tells us how to graph. So the degree, we've said a couple times, is 4, which we care mostly, again, that it's even. And then our leading coefficient this time is 2, and we care positive or negative, so that's positive. So without talking about the middle of the graph, an even degreed positive leading coefficient polynomial tells us the ends both are going to go up. Good. Yep, if it's odd, they would have gone opposite directions depending upon whether the coefficient was positive or negative. So just a rough sketch here. On the x-axis, I'll only be able to show 2 zeros because when we create our graphs, we're graphing on the real number plane. If you're interested, there are math classes where you graph on the imaginary number plane, but we won't do that in this class. So that's why visually we'll only see these 2 zeros at x equals -1/2 and x equals -2. And then based on the end behavior, I know on the left side of the graph I need to be shooting up. On the right side of the graph, I also need to be shooting up. And the multiplicity of each of these zeros is technically 1. None of the factors were repeated. So I need to cut through at my 2 real zeros. So at -2, since I already show the line above the x-axis on the left, it must cut down below, and the vice versa on the next 0. So this one ends up having kind of more of a quadratic shape, which is normal for an even degreed polynomial to look quadratic. Sometimes there's more happening in the middle to make it like a W, or I mean, we could have something crazy like that depending upon the degree. But this is a degree 4 polynomial with 2 complex zeros, or 2 imaginary zeros, and 2 real zeros. So that would be a decent enough sketch. So I think that's pretty much all we're doing in the last couple homework problems. I hope this clarifies the process for anybody who chooses to watch this discussion. Paula, anything you want to chime in or add to help your peers? Yeah, I'm glad we got to work through a couple together. So this should help out with any folks who are still wrapping up the homework. And then, of course, by tomorrow, you all will take quiz 4, which will be similar problems to these. Cool. Yes, thank you. I'll be on, yeah, you too. I'll be on at 3:45 if you have any other questions too. Okay. All righty. We'll see you soon. Bye.